Alright, welcome to your first current electricity chapter tutorial. A very easy chapter, guys. It's got a lot of basics in it, and you can score easily in this section in the paper if you know all those basics. And you are asked a couple of numericals also, very typical numericals, even in the board paper. So don't miss those out. They're very crucial marks in the paper. I'm just gonna start off because there's a big time constraint. So guys, what is the concept of current? Current is just the rate of flow of charge. So if I've got charge, what this line actually means is that if I've got charge, which is denoted by Q, then the amount of charge that's flowing through a conductor, right? Now, I'm pretty sure you know the circuit, how you draw it, the positive and the negative terminals. So if I've just got a conductor, guys, and the amount of charge that's flowing through it in 1 second, that's the Q by T, which is the amount of charge is flowing through the conductor per second. So this is what current is. So guys, that's the basic of what current is. So this is something that you really need to know. You're not going to be asked such simple questions, but the only thing that you can be asked here is what is the current. So the basic definition is that current is the rate of flow of charge. So if you've got a conductor, then the amount of charge which is flowing through the conductor per second or in 1 second is called as current, and current is denoted by I, guys, which I was just using. So we say I is Q by T. SI unit of I is ampere. There was a guy named Ampere. You'll use next year if you take sciences. And Q is just charge, and its SI unit is coulomb. And T is very famous indeed. So it's time, sorry, and its SI unit is second. So guys, this is the basic of current electricity. So you should be knowing this by now. I hope you do know this. So as we say that coulomb per second is what ampere is. So C by S is it's also denoted as C as -1. The -1 is nothing but if you've done exponents, then the S -1 becomes an S positive 1 in the denominator. So this is just I, or I'm sorry, it's not I, it's ampere, so it's A. So here he's just talking about the unit of current, which is ampere. Now I'm referring to concise, guys, and I'm really rushing through this because I have to finish this real fast. So guys, when he's talking about units of current, he's also talking about milliampere. Now don't get confused. In class 9, if you remember, first chapter that you had was, I think, dimensions and units. So there, you had mega, giga, tera, peta, exan, femto, atto, and all of those. So milli was another one of them there, if you do remember, milli and micro. So micro is nothing but 10 to the power -6, and milli is nothing but 10 to the power of -3. I'm pretty sure you've used this notation a lot of time when you say millimeter or milliliter. That's just 10 power -3, and this is standard notation, guys. So wherever you encounter it, whether in your chem paper, physics paper, or any other paper, then it's 10 power -3. In micro, it's always 10 to the power -6. So there you go with this thing. Now, guys, another notation is I equal to Q. Again, I'm just gonna revise this. I is nothing but current. Its SI unit is A ampere, which is coulomb per second, because charge is coulomb and time is second. So Q by T is C by S, which is ampere. So guys, I is Q by T, and charge is nothing but as the number of electrons that have passed through the cross section of a conductor in time T. So guys, if I have n number of electrons that pass through um, a conductor in time t, then guys, I'm pretty sure you'll be knowing this, that electron has a charge of 1.6 into 10 power minus 19 C. The C is nothing but coulomb. So guys, if I have n electrons, then the overall charge is n times E. That's nothing but E here is, guys, the constant. E is the charge on one electron. Alright, so if I've got 15 electrons, then the overall charge is 15 into 1.6 into 10 power minus 19. If I've got 20, then it's 20 into 1.6 into 10 power minus 19, divided by the time taken by this much charge, this charge to pass through the cross section of the conductor in time t. Alright guys, so very basic. Now let's just move on to, I'm sorry, to the convention of current, like the direction which we usually take when we're indicating current in a circuit. So guys, this is very basic. In fact, I'm pretty sure you'll be knowing this already. This never is tested in the paper, but you should be knowing that in older times, when we didn't know the concept of electron and charge and all of that, we always used to take positive as the positive guy and negative as the negative guy, in the sense that we used to say that if we have a ball here, I don't know if you guys done work power energy, I really doubt it, but you should be knowing this. If you have a ball here, and if the ball falls onto the ground, this is the ground, then guys, this point is taken as higher gravitational potential. This is very easy, basic. Don't get confused by the fancy words. They're not at all fancy at all. I'm sorry. And this was taken as lower gravitational potential. So we always said that a ball, which when it falls from a certain height to the ground, then this height, the potential possessed by this ball over here at this point is always the higher potential, and right here is nothing but the lower potential. So we always used to say the ball always falls whenever it falls from a higher potential to a lower potential. Same way, guys, if I have a beaker here, all these examples are given in your book too, and they're connected this way, and there is a beaker, another beaker which is lesser water in it. Now, if you observe, if these two are openings, and if you observe after 10 minutes or 15 minutes, then this water over here will pass through this pipe, and after 10 minutes, this water will fill up to a certain height till this point, and when this water is moved down to this vessel, even this will have a height which would be somewhere around here. So guys, they will have equal heights. So whenever we talk about, observe this, in fact this is an observation, a very cool observation, that whenever you have two beakers, then the water always moves from another higher potential to a lower potential, so, or a higher height to a lower height, to attain a same height. So guys, this way. Another example was temperature, that if you have a hot body and if you have a cold body, you make them or you put them in contact, then the hotter body transfers the heat to the cooler body. So that's about it. So which is why we took that charge or current always flows from a positive to a negative terminal. Now that was again a convention, guys, but this was actually not true. um, I will be telling you this later, I think, because according to the book, this is not how I should be moving. I will come down to something known as potential now. Now potential, guys, is nothing but as the book says, um, potential is the electrical state of a conductor, which just simply determines the direction of flow of charge. Right? So it simply determines the direction of flow of charge. For example, if I have a body here and if I have a body here, so potential between these two bodies would just determine whether, and both of them are charged. For instance, if this is a negatively charged body, so it has an excess of electrons, guys, and if I have a comparatively positive body, so this is comparatively more positive than this body. So potential between these two would just determine whether charge would flow, whether current would flow, or flow of charge would be from left to right or right to left. So that's what potential between these 2 points determines. So all this happens whenever they're placed in contact, like they're right next to each other. For instance, this body was right here, or if they're joined by a metallic wire. Now, this case I've joined it by a metallic wire. So, what would the potential between these two bodies tell me? Now, guys, when I was talking about conventional current and what the direction is taken conventionally, I know teachers and even circuits, they usually denote that here if it is a positive and this is a negative, and you have a resistance, and they're joined by a key and all of that. So my basic point here is that you always take direction as this way. You make arrows, and then you say that, yeah, this is positive, so this is negative, so current always moves from positive to negative. Now that's conventional, guys. Actually, much later, when we came to know, when people, not us, when people, they discovered, what they found out was that current actually moves from the negative terminal to the positive terminal. So it's the other way around. So guys, this is taken as the conventional direction of flow of charge, which is from a positive to a negative. But what actually happened was the other way around. That flow of electrons or flow of charge was actually from the negative terminal, which had an excess of electrons, to the positive terminal, which had a deficit of electrons. So guys, now this is what is called, this body is known as a body which has a lower potential. So can you see it? That when I was discussing about higher gravitational potential and higher temperature or higher level of water, so what we used to think was that positive, negative, so higher potential to lower potential. So this is what was the conventional direction of current or flow of charge. But now later, when we found out, it was this, that it actually moved from a low potential to a higher potential. So that was the basic difference, guys. You might be asked a question here. So this is just a concept. You have to get it inside your mind. I will now be rushing and moving on to potential at a point. Guys, I can't do this. I can't explain everything to you in electric potential, because even I don't know so much about it. I'm just a kid in 11th, 1 year senior to you. So don't trust my opinion at all on the basics of electric potential. So I'm not going to be discussing them with you. I'm just going to be moving on to definitions, guys. On page number 187 in my book of concepts, we have potential at a point, which is defined as the amount of work done in bringing a unit positive charge from infinity to that point. So, guys, this is something that you must understand. I'm really sorry I can't do this in this tutorial at least. So what you should do is just approach your teacher if you can't understand something in this. However, if you really can, then it's amazing, because that's quite something to do if you can understand this all by yourself. So guys, just remember this definition, that potential at a point is defined as moving a unit positive charge, which is also known as a test charge, if your teacher has already told you. And I really think, if because you're doing all these tutorials for first examinations, then that you've already passed through tests on this. So I'm sure you've done this. So that way, that saves my time too. So this is a unit positive charge, also known as a test charge. It moves from infinity to this point, right? So the amount of work done in bringing this unit positive charge from infinity, that's the sign of infinity, to this point, guys, is known as the potential at this point. Right now, that's all I can tell you right now on this bit. So what we have is V, which is nothing but the potential. Volts, it's known as, a scientist named Volta. So it's volts, and it's denoted as work done in bringing unit positive charge. So this is another formula, you may call it, or something that you have to understand and learn at some point of time. So guys, just remember that V is equal to W upon Q, and W has units of joule, I think, if I'm right, and charge has coulomb. That's its SI unit, as I just told you earlier. So joule per coulomb was taken as volts, which was V. So guys, 1 volt is equal to 1 joule upon 1 coulomb. Now that's again something that you have to learn. Now, when I'm done with potential, now I'm going to be moving on to potential difference. Again, guys, something that I can't really explain. You've got to do it yourself. However, let's try and understand what potential difference actually means. So, guys, potential difference exists between 2 points, and the definition goes something like this: that potential difference between 2 points is defined as the work done in moving a unit positive charge, which is also known as a test charge, from one point to another. So it's just different from potential in the sense that you have 2 points here, and potential difference exists between these 2 points, and it's known as the amount of work done, which was again W, in moving a positive charge from one point, which is, let's take as point 1 and point 2. So if I move a unit positive charge from this point to this point, then the amount of work done in moving that amount of charge is known as the potential difference. Guys, potential difference between these 2 points. Another definition that you have to learn after your exam. Now let's come on to something which is really interesting. I know, I'm pretty sure you know what is the concept of resistance. Resistance, guys, is nothing but the obstruction, or it's just like an obstacle, you know. So obstruction offered to the flow of current. If current is flowing this way, and for instance if you have some obstruction here, so and then it still flows here, so the obstruction which is offered to the flow of current is nothing but resistance. Resistance is a very common word if you're a Terminator fan, and I love resistance there also. However, let's not get confused. And this resistance is just offering an obstacle, a problem to this flow of current. So that's about it. Let's move on to what are the factors affecting resistance of a conductor. First and foremost, this question is actually the favorite question um, of teachers, because they ask it in almost all examinations because they really want to test this concept. So please pay attention. I'm really sure they've done this before, but in case you're having problems, then I will be explaining this. So nature of conductor. What does this mean, guys? It really means that, you know, when you have different metals, and different metals, they have different, as I said, concentration of free electrons in them, and therefore, you know, this is what determines the resistance of a conductor. I'll tell you how. For instance, if you have metals like silver, copper, or aluminium. Why did I say that? It's aluminium. I'm sorry. Silver, copper, aluminium. You know, substances like this, they offer very less resistance. So resistance in this case is almost in silver actually it's almost nil. But so what my basic point here is that these are actually called good conductors of electricity. So now if you can remember that good conductors of electricity offer very less current. Okay, so conductors, they conduct electricity, and since they offer very less resistance, therefore they don't need conductors of electricity. On the other hand, substances like rubber, wood, you know, glass, plastic, substances like this, they offer a lot of resistance, and they're known as very bad conductors. However, they save us sometimes um, when we wear rubber chappals, and you know, whenever we touch wood, when we're dealing with electric current, then they actually save us from getting electrocuted. So guys, that's about nature of conductor. Now let's move on to the length of the conductor. So when I say that electron, when traveling in a conductor, you know, it collides with different fixed positive ions, as stated in our concise book. You know, so more the number of additions, obviously more the resistance. So if I have a long conductor, then I have my electrons, which is just charge. Electrons consist of charge, guys. So that's what they so electrons are basically the charge, you know. So electrons, when they're moving in a conductor, and they come across different fixed positive ions, right, and several other particles, then obviously these positive ions, they offer resistance to the conductor, to the electrons, and they actually collide with them, and that's what resistance means. So more the length of the conductor, more the and so more the resistance, guys. Length, you know, it's directly proportional to, I'm sorry, resistance, guys, is directly proportional to length of the conductor. So more the length of the conductor, more the problem, and more the resistance. However, in another case where I'm talking about area of the conductor, same thing. Ooh, got a big conductor here. So the electrons which are here, they've got a larger space to move. So if there are positive ions, then this one might just say, okay, take a turn, and then just move on. So if they have free space, if they have more space, then comparatively your resistance is less. So if you're, I'm sorry, if in case you have a larger or a thicker conductor, resistance is inversely proportional to the area of the conductor. So that's pretty much about how resistance depends on the thickness of the conductor. Now let's move on to temperature of the conductor. Nothing much, just the temperature when it increases, so the random motion of the electrons increases, and there will be number of collisions which will increase, so therefore the resistance of the conductor will increase. So temperature, and they get excited, ooh, yes, they want to move around. So electrons, when they want to move around, obviously there will be more number of collisions when they're excited. So the resistance is directly proportional to the temperature of the conductor. So that's pretty much about it. Do I have time? I think I'm just gonna take another 1 minute. Guys, Ohm's law, please learn this, very easy and one of the basic things in this chapter. So Ohm's law, guys, German scientist named George Simon Ohm. You don't need to know that. Only thing you need to know is that the current flowing in a conductor is directly proportional to potential difference across its ends. And the only thing that this means is that if the potential difference between the two terminals in a circuit, or you know generally between the two terminals, if it is increased, then the amount of current that will be flowing will also increase. So that's what Ohm's law means. So that's about it. I is directly proportional to V. It's really hard to explain this, guys. Um, so if I have another circuit, I'm going to do this again with you. If I increase the potential difference across these two terminals, then obviously the amount of current will also increase according to this relation. So this is the only relation that you need to understand. So if I say that I is directly proportional to V, now I don't know how many of you can understand this, but then V by I will be equal to a K. Now K here is nothing but a constant of proportionality, or not even proportionality, I'm sorry, it's just a constant. So if I have V by I is equal to a constant, then I can say that V is equal to I K. Now you don't even need to know this, but if you in general have V is directly proportional to I, then if you want to remove this proportionality sign, I'm really sorry, then you just you just incorporate in this relation an equal to sign and another constant. So I may say V is equal to IK. Now I don't really say K, but I just make it an R and tell you that R here, guys, which is resistance, is nothing but a constant of proportionality. So whenever you remove this sign, proportionality sign, you just um, induce a constant of proportionality into this relation. So that's pretty much about the Ohm's law thing. One thing that you must remember, and another question that may be asked, is in Ohm's law, all of this, like whenever you have a current flowing in a conductor which is directly proportional to the potential difference across the ends of the conductor, this is only true provided the physical conditions and the temperature of the conductor remain constant. So if the physical conditions and temperature, they're not constant for the conductor, then this law will not apply or hold. So that's pretty much about it. Our unit of R is, guys, it's Ohm. George Simon Ohm, as I already told you. And you know what R is according to the relation V equal to IR, very very famous, as we just derived it. V is equal to IR, so R is equal to V by I. V is volts and I is ampere. So R is volt per ampere, which is nothing but ohm, guys. So this ohm is also known as omega, and that's what you call resistance. 2 3 units that you must remember is kilo ohm, 10 power 3 is kilo, alright. Then another is mega, which is 10 power 6, and I think that's pretty much all they ask about. So 10 power 3 and 10 power 6 ohm is something you need to remember. This is kilo, this is mega, and there are other giga, tera, peta, and all those. So you can learn them if you really want to. One last thing, guys, conductance is nothing but reciprocal of resistance. So conductance, if and a lot of times there are questions, what is conductance? Now I used to get confused myself in the paper because I really don't know what to say. So I used to make up something, and in the end I used to say conductance is the reciprocal of resistance. Now all that you have to write is just that conductance is reciprocal of resistance. However, if you can explain it in your own words, it's very good because our teachers really encourage that. Now guys, that's pretty much about it. I think I'm done with this tutorial. At least I'll be moving on to the next tutorial, and in that I will hopefully finish this chapter, and then we'll move on to household circuits. Thanks for watching, guys, and sorry for not being prepared and just doing this first shot. Thank you, guys.